Okay, we're continuing with more example problems from the Taylor and Maclaurin series section. In this video, we're going to evaluate two definite integrals using infinite series. So using the Taylor series representation of the integrand. Okay, now to do this, you might ask, well, okay, are we going to use the Taylor or Maclaurin series, or like, where are we going to center the Taylor series? You can center it wherever you want. Because remember, it's not like if you have e to the x and you have its Maclaurin series, you get some power series. It's not like if you have something that's like centered somewhere else, you get some other e to the x here. It's still just e to the x. So you can use whatever you want. Now, you need to look at the limits of integration, though. It's not like you have to have the center point be within the limits of integration. However, that you would need that to be the case, it depends on the resulting radius of convergence. You need the radius of convergence to fully encompass the limits of integration. But if we evaluate this function, if we knew the radius of convergence was going to be infinity, then you could use whatever you want, whatever is simplest mathematically. So, which usually is the Maclaurin series. Okay, now I'm curious if this, whenever we did indefinite integrals as power series in the previous video, we were given integrals that we couldn't get by normal means. We couldn't get the indefinite integral, even with a calculator. So I'm curious. I wonder if we could get the answer with a calculator. Okay. So go from 0 to 1/2. So yeah, it does give us the exact definite integral, but you could imagine like there's definite integrals that you potentially can't evaluate. And so, but you have more options with a definite integral. You could use numerical integration because a definite integral it's comes down to an area under a curve, so you use like numerical approximations for areas under curves, right? When you think about it as it's whatever integrand is the function with respect to the independent variable, and so you think about calculating the area under that curve numerically, or you could do a power series integration, definite integration, and get an estimate. So, and that's what we're going to do here, because we're going to just give the answer to 4 decimal places. We're not going to be getting the exact, we're not going to be getting the exact definite integral. So yeah, so let's get into this. First, we want to just come off to the side and get this indefinite integral. That's the first thing we're going to do. So, okay, arctangent x. We have arctangent x here. We'll use that as a base and build off of this. So minus 1 to the n, x to the 2n plus 1 over 2n plus 1. Okay, so we've got the function x cubed so this is x cubed minus 1 to the n Okay, so yeah, this is arctangent of x as a power series, or it's Maclaurin series, and we've multiplied both sides of arctangent x by x cubed. So now let's bring in the x cubed. Okay, so x to the 2n plus 1 times x cubed is going to be x to the 2n plus 4. Okay, now let's get the radius of convergence. Just we need to check, right? Just to be sure that it's going to be valid to do this definite integral. And unfortunately, it's not. We brought in this outside x cubed, so we can't just match this up with the radius of convergence of arctangent of x. At least I'm not sure if we can or not. So let's do the ratio test, which is not that big of a deal. Ratio test is easy, it takes some time to do it. So, okay, 2 times n plus 1 plus 4. That's 2n plus 2 plus 4. That's 2n plus 6. So, okay. X to the 2n times x to the 6th. All right, now 2 times n plus 1 plus 1. 2n plus 2 plus 1, 2n plus 3. Okay. Now we've got 2n plus 1, and then x to the 2n times x to the 4th. Okay, x to the 2n. Okay, so this is all with this x squared and just these n terms. This is always, everything that's left over is always positive. So we can take off the absolute value. Okay, as n goes to infinity, what does this go to? This goes to 1, so you're just left with x squared. When is this less than 1? Well, that's going to be between, this is a quadratic inequality. That's going to be between, the radius of convergence is 1. So here r is 1. Now, can we work with this? Yeah. So anything from minus 1 to 1, where the limits of integration are between minus 1 and 1. Okay. So the integral of x cubed is equal to, so we've got c plus, okay, so x to the 2n plus 4 plus 1, that's x to the 2n plus 5 over 2n plus 5. So we've got, so 2n plus 1, 2n plus 5, and then x to the 2n plus 5. And the radius of convergence doesn't change. We just integrated. So, okay. Now, there's the indefinite integral. When we're integrating from 0 to 1/2, the idea is that, like, you plug in 1/2 here, and then you subtract that from plugging in 0 here. And so the constant of integration doesn't matter. Now, when you plug in x is equal to 0, you get, this is 0 for all, every term is 0. So what it comes down to is that this is equal to this series with x equal to 1/2. So we've got 1/2 there we go. So, okay. So now this is turned into a problem, a type of problem that we worked in the first half of the chapter. This is just an a sub n now. There's no x involved. And, the a sub n is not something, usually with most series like this, we can't find like an s sub n here and take the limit of the actual s sub n formula and find, the exact value of this infinite series. Well, that's assuming it's convergent, but we know it's convergent because we plugged in a value that was within the radius of convergence of the series. So we know it's convergent. So we don't need to prove that it's convergent. But in general, since we can't find we know it's convergent, but we're probably not going to be able to find, at least with what we know, what we've learned so far, we can't find the exact sum of this series. Well, how do we get this accuracy? Well, this is exactly what we did in the first half of the chapter. We're going to use a method. We need to prove convergence again, just to show that this series is applied to a certain convergence testing method. Then we're going to use that r sub n size estimation technique from that convergence testing method. So, okay, so let's just act like we don't know that this is convergent. How would we test this? Well, we see it's an alternating series. It should be alternating. So this could never be positive. This is always positive. So yeah, it's alternating. So the first is alternating series test. Okay, so alternating series test. How do we do the alternating series test? Well, we need to make sure that this is applicable for the alternating series test. And so this is what we do is this is the B sub n, right? The absolute value of the alternating series is the B sub n. We have to make sure that the B sub n is decreasing, and we can see it definitely will be, because we can rewrite this as 2 to the 2n plus 5 right? And that is always decreasing for all n as n goes to infinity. So, okay, with that, we want to take the limit as n goes to infinity of this B sub n. Well, we can see that's going to be equal to 0. Okay, so it's convergent, but we already knew it was convergent. But still, we wanted to do that because we want to use the R sub n estimation theorem for the alternating series test. We want to make sure that we don't, the test isn't inconclusive or something for the series we're dealing with. Okay, so how do you estimate the size of the R sub n with the alternating series test? Well, it's the absolute value of the R sub n. It's absolute value because this we have negative terms that could be above or below the actual value. So remember the R sub n is this is the sum of the infinite series, the exact sum S, which is equal to S sub n plus R sub n. Right? If you do a partial sum, you sum the first 50 terms, you get an estimation for the infinite sum, which remaining is the R sub n. So it's S sub 50 plus R sub 50, for example. Okay, well, for the alternating series test, this is going to be, the magnitude of this is going to be less than or equal to B sub n plus 1. Again, this is A sub n, and then the absolute value of A sub n is B sub n. Okay, and so what it's saying is that whatever you choose, if you sum the first 50 terms, then the sum that you get is going to be, if you take B sub 51, it's going to be within B sub 51, above or below the actual sum. And so just to show you the S sub n is what? Let's write what S sub n is. So all you do there to write the S sub n, you just take the infinite series and you replace the n with an I, so that you can, because you're not going to infinity, you're going to n, and that's it. So it's minus 1 to the I like that. Okay, now we want to type in the B sub n into the calculator. So 1/2 to the 2 times n plus 1 power divided by 2 times n plus 1 divided by, okay, let's see, 2 times n plus 1 times 2 times n plus 5. So we want to do this divided by this. Okay, and that we'll store as E. Okay, so there's the B sub n. So now what we want to do is we'll take E. Well, actually, let's do this. Let's take E and store it as B, because we're going to be using the A sub n later. So there's the B sub n. So let's take B with n is equal to 3.0001. But this wants 4 decimal places, so we need to keep going. Let's do 5. So that's 4 decimal places, but let's make sure that maybe 4 would have been enough. Okay, yeah, so we can do n is equal to 4. Well, no, yeah, this is b sub n plus 1. So that means that if we do n is equal to 3, s sub 3, then we'll be accurate to within this much, which is better than 4 decimal places. So we want to do s sub 3. What is that equal to? So we want to do minus 1 to the n times b, and that's going to be equal to a. That's what we're summing. So we want to do a with n is equal to 0 plus a with n is equal to 1 plus a with n is equal to 2, and we're going to all the way to 3 plus a with n is equal to 3. Okay, so that's not right. Let me type this in again here. So, okay, 2 to the 2 times n plus 5 times 2 times n plus 1 times 2 times n plus 5, then 1 over all of that. That is the b sub n. Okay, and then if you do minus 1 to the n times that b sub n, we're going to store that as a. And so, okay. Now if we do b with n is equal to, let's say, 2, that's actually better than 4 decimal places. So we just need to go to s sub 1. So it must have messed something up. Okay, so a with n equal to 0 is that, plus a with n equal to 1 is that. There we go. Okay, so I must have messed something up. So 0.005878 plus or minus and 0.000043. Okay, and we can go ahead and, so x cubed times arc tangent x. Okay. And that's the exact answer. Let's subtract 0.1234443. Yeah, you see, we're within, we're right above this. So there you go. Pretty cool. Okay, same type of problem. Let's start by writing this integrand as a power series. So we're going to use the binomial series here with k is equal to 1/2 and x is equal to x to the 4th. So Okay. Okay. So, yeah, here's the binomial series. So we just replaced x with x to the fourth, and k is 1/2. Now let's write this out. So the first term is going to be 1. The coefficient is 1 times x to the 0. Then it's going to be plus 1/2 times x to the 4, because the coefficient is just k, and it's x to the n, or in this case, it's x to the 4n. And then we should have minus here because we have 1/2 times 1/2 minus 1. That's, yeah, so that's going to be, you'll have 2 times 2 times 2 factorial, and then a 1 up top. And then this is x, the n is equal to 2 here. So that's x to the 8th. Okay, then plus, what is 1/2 minus 3? So that's going to be 6 over 2. That's minus, or no, would it be 1/2 minus 2? Yeah, 1/2 minus 2. Because we're here now. So 1/2 minus 4 over 2, that's minus 3/2. So, but you have minus 3/2 times minus 1/2, that's positive. So you've got, it's going to be 2 times 2 times 2 times 2 factorial. And then you'll have a 1 times 3, and then this would be x to the 4 times 3. Okay, then 2 times 2 times 2 times 2 times 2 factorial, and this is going to be a 5. X to the 16th. Okay, so this is equal to, we could do 1 plus 1/2 x to the 4th, then plus sum from n is equal to 2 to infinity, and then we want to put the alternating term here. The first term is negative, so n minus 1. Okay, and then we're going to have 1 times 3 times 5 times, and then we'll have, and this is going to be an arithmetic sequence starting at 1 plus increasing by 2 each time, and then n minus 2. The starting n is 2. So 1 plus 2n minus 4 is equal to 2n minus 3. So this is going to be 2n minus 3. Let's see. So when n is equal to 2, you've got 1. When n is equal to 3, you've got 3. And then when n is equal to 4, you should have 5. Yeah, that's right. Okay, now over, so we've got 2 cubed here, then 2 to the 4th, then 2 to the 5th, because 2 factorial is 2. So we're starting at 2 cubed, so it's going to be 2 to the n plus 1. Actually, that's it in the denominator. Okay, now x to the should be just 4n. Okay, and actually, I'm not sure, I don't know what I'm doing here. This should update each time. This is 3 factorial, 4 factorial, etc. So what you've actually got is, it's going to be 2 to the n times n factorial. Okay, that's 1, the square root of 1 plus x to the 4th. Okay, now the radius of convergence, the binomial series converges for, it has a radius of convergence of 1. Now we substituted x to the 4th for x, so that means that a radius of convergence of 1 means this. Okay, but we substituted x to the 4th, and if you solve this absolute value inequality, it's just going to be x is between 1 and minus 1, so this is going to have a radius of convergence of 1, and that's important because we want to track that, because we want to compare that to the limits of integration. Okay, so now let's integrate both sides here. Okay, so you've got x plus, let's see, 1/10 x to the fifth. You bring in the 5, you get 1/2, right? Plus, okay, we're going to have minus 1 to the n. And then, let's see, x to the 4n plus 1 over 4n plus 1. So 4n plus 1 times 2 to the n times n factorial. And then 1 times 3 times 5 times x to the 4n plus 1. And there's also a plus c. Okay, so now when we're integrating from 0 to 0.4, so you plug in, the c doesn't matter with a definite integral. So you plug in 0. Let's see where this starts. N is equal to 2. You have x to the ninth. So there's an x term in every single one of the terms of this series. So when x, if you plug in 0, this is 0. All this is 0. So the definite integral then is equal to, well, we start with x. So is just equal to plug in 0.4. So, okay. Okay, 0.4. There we go. Okay, now, so this is an alternating series. You know, this is always going to be positive. But to use the alternating series remainder estimate, we need to verify that this is applicable for the alternating series test, and that means that the b sub n, where you just take off the minus 1 to the n, that needs to be decreasing for all n. We're not going to go through a full, official proof to show that this is decreasing for all n, but what we're going to do is, so, okay, let's type in 4 times n plus 1 times 2 to the n times n factorial, okay, 1 over that, okay, times 0.4 to the 4 times n plus 1. Okay, let's store that as b. Okay, now I realize we haven't done anything with this numerator yet, but okay, so now let's do b with n is equal to 2. Okay, and then that'd be just times 1. So, okay, that's b sub 2. Okay, now let's do b with n is equal to 3, but then we'll multiply this times, this would be, the numerator would be 3. So there is b sub 3. Now let's do b with n is equal to 4, and then this would be 3 times 5 is 15. Let's do b is equal with, or n is equal to 5, and you would have 5 times 3 times 5 times 7. Okay, let's keep going a little bit. And it's equal to 6. So 3 times 5 times 7 times 9. Okay, now we can actually come straight to this list here to see how many terms we need to use from this series to get the accuracy we need. So this is b sub n, this is n is equal to 2, 3, etc. And we see that actually n is equal to 2 is 4 times 10 to the minus 6. That's less than 5 times 10 to the minus 6. And that represents b sub n plus 1. So we don't even need to use a term from this series. Did the first two terms, that would be accurate to within 5 times 10 to the minus 6. That's interesting. Why is that? Because, okay, this is an exact integral. Like, well, all of this is an exact integral, but like as far as the first two terms, there's no error here. There's no error in any of this. There's only error that comes in the fact that you don't include all of the terms going to infinity. So in other words, if we used n is equal to 3 here, this would be the error. Well, the error would be within this much from the actual sum, the actual definite integral. Well, once you add on these two values, you still have the same error magnitude. It doesn't change anything. So the point is that, like, okay, what's happening is each term of this series the magnitude is very small. If you find this confusing, that's what's happening. So once we add this and this, each of these terms is very small. Very small. So if we omit all of this, this as an infinite sum is going to be, I think that's the idea. That this as an infinite sum is going to be less than 4 times 10 to the minus 6. That's the way you can look at it. So, okay, all we need to do is get, so 0.4 to the 5th divided by 10 plus 0.4, 0.401024 plus or minus 4 times 10 to the minus 6. I'll write it this way. There we go. So let's actually get the exact, let's check that. I might have checked this already, but let's do it again. So we'll store this as E, and then going from 0 to 0.4, E 0.40102, let's add there you go. We were actually exactly 0.04 times 10 to the minus 6 below the answer.